I can fade out the music whenever you're ready.
Give me 1 minute. Oh, I can start with your bio.
Sure,
Yeah,
that sounds
it's
great.
good.
Yeah,
Okay. Yeah, thanks that joined to our seminar. I really appreciate that you accept our invitation. We hope so to have more seminar and connection with you and your team in near future. And for audience, Katanya Kuntz is a founder and CEO of Cubo Consulting Corporation and a research associate at the Institute for the Quantum Computing, University of Waterloo, Canada. Cubo Consulting helps businesses, nonprofits, and government organizations make informed decisions about emerging disruptive technology, but training businesses, leaders, and the future quantum workforce on quantum technologies. She is also the KISAT Science Team Coordinator for Canada's first quantum satellite mission, Quantum Encryption and Science Satellite, KISAT, which will demonstrate the distribution of encrypted keys, quantum key distribution, between ground and space. Katanya received her PhD in electrical engineering, quantum optics from the University of New South Wales, Australia, in 2013, and BS in physics from the University of Calgary, 2008. She works in the field of experimental quantum optics, such as generating quantum state of light using laser and nonlinear crystal to study quantum entanglement. Okay, you can start whenever you want.
wonderful.
Okay,
Thank you
it's
very
good.
much,
Okay.
Mohammed, for that introduction. And I'll share my screen. And I'm just going to make you guys back over here. Wonderful. All right, how does that look? Good, wonderful. Thank you again, and thank you to the organizers. These seminars are a great way for us to all connect. And since I'm located out in Alberta, Canada, so a little far from you, so instead of flying over, I'm going to beam in via the internet. So today, it's all about an introduction to quantum technologies. What do I mean by these technologies? I mean quantum computers, quantum sensors, quantum materials. The actual devices are made out of quantum materials, so that's kind of fundamental pillar for all of this. And also quantum communication. As you heard, I'm part of the KeySat mission, so that's literally doing quantum communication with satellites. So, hello again. In case you haven't met me before, my background is experimental quantum optics. I'm the founder and CEO of Cubo Consulting, and I offer training and consulting in both technical and non technical audiences. And if you're unfamiliar with what I mean by quantum optics, this is an experiment that I worked on when I was at the University of Calgary. Technically, this is a classical experiment, but it has all the same elements of what our quantum experiments look like. A big laser, in this case, a very scary 1 watt green laser. It was so bright that we put a little bit of smoke into the air, and you're able to see the beam in free space. So usually you can't see lasers in free space unless there's something to scatter the light and show you that beam. And the whole point was to make this very narrow beam that you see here pointed out called a lightsaber. It's actually a Bessel beam. And so this lightsaber here, you see the beam just kind of diffracts away, just disappears at the end. So there's a very special mirror behind this glowing box cube here on the right, and that mirror is a conical shaped mirror. And because of the way the light reflects off of this mirror, it then does it's called a self-replicating beam. or a non-diffracting beam. And so you can see the beam of light maintains the same intensity, the same size over a set distance, here almost a meter. And then once it reaches the end of that interference effect, the light will then just diffract away. So that was one of my first experiments, and of course you always have to wear laser safety goggles when dealing with bright lasers. So today, yes, we are going to be talking about quantum physics, but don't worry, if you're not an expert in this field or you're unfamiliar with these topics, please keep an open mind, ask me lots of questions. I promise to keep it at a level that everyone will understand, and we even have some little technical deep dives available if the appetite is there. So overall, and I love questions, there's lots of places I've put into my slides to stop and ask for questions, but Mohammed, if you want to keep an eye on the chat or use the Q&A box, I see there's quite a few people in the audience, that's great, the virtual audience. So if you want to either put them in the chat, or if the chat gets too busy, put them in the Q&A box, and make sure I answer all questions, because that's really important. Questions are so fundamental to your learning. So today, like I said, this is an overview of all quantum technologies. I'll start off by defining what is a quantum computer, a qubit, very important topics like the quantum threat and what is Q-Day. Then we'll have a little deep dive, not too technical, I promise, about the Nobel Prize in Physics from last year in 2025. That topic is very fundamental to all of these technologies, so it's very interesting. Then I'll go through some quantum communication. What is the quantum internet? Maybe you've heard of quantum key distribution. I'll talk a little bit about what that is. And then we'll finish up with sensors. So what is a quantum sensor? And then there's these devices called magnetometers. So there's a SQUID. So this has to do with superconductivity, which is related to the Nobel Prize. And also NV centers, nitrogen vacancy centers. So these are just two examples of quantum sensors that are very compact, portable, very attractive for a lot of different industries. And so I just want to give you an overview, a taste of that. All right, so first, what is a quantum computer? Well, if you're unfamiliar with this topic in general, let's take a step back. What is quantum? So quantum refers to quantum physics, the physics of the tiny. So this is also called quantum mechanics sometimes. That's the mathematics behind the physics. And so it's the study of the smallest particles and energy of our universe. This is like atoms, ions, photons. You'll hear me say photon a lot. That's a particle of light. And on this tiny scale, matter and energy just behave differently compared to our classical world that you see with your everyday eyes. And because of this, we have to use this different mathematics, quantum mechanics, to explain it. And there's some really weird stuff, like entanglement, superposition. These are things that just don't exist in our classical world. But they definitely exist in our quantum world, and these quantum technologies I'm going to talk about are harnessing those very interesting properties. Now, you might have heard about this quantum 2.0 or the second quantum revolution. We've already had a quantum revolution, if you didn't know. The computers that we use today with the transistor, also atomic clocks used for GPS, these are all forms of quantum 1.0 technology. These technologies operate on the principles of quantum physics, but they're not necessarily using individual particles to do the computing, the sensing, the communication. Whereas quantum 2.0 technologies, now we are using individual atoms, particles, photons, the spin of a particle to do these computations, to do the sensing. And so that's why we distinguish it to this new technology, the second revolution. And before I get too far, I just want to get this one out of the way. AI is not quantum. There's a lot of people that think those two things are the same. And they are not. So artificial intelligence is a classical technology. It's a collection of classical traditional computers, like I use right now to talk to you on the internet. They process information still in a 0 or 1 as a bit. And so this is all classical. So AI is not quantum. So now what is a quantum computer? So now we're going to use quantum bits, and that means like an atom, an ion, something that's a quantum system. And that's going to be used to store and process the information. And because it's a quantum system or a qubit, it can exist in this weird superposition state of both 0 and 1. And you might have seen like Schrodinger's cat. This is a thought experiment back in the 1930s to try to explain like this weird combination state, superposition state that quantum systems can be in. It's almost like a cat could be both dead and alive at the same time, unless you measure it, unless you observe it with your own eyes to see which is what it is. And so in this theoretical box, this hypothetical box, you have like a vial of poison, there's a hammer over top, and that hammer could break at any moment. And that hammer falling is probabilistic. And so as time goes on, it becomes more and more likely the cat will be dead. But you don't know until you open the box. And so this is to, again, illustrate this weird superposition principle that just doesn't make sense in our everyday world. Cats don't just walk around half dead, half alive. But a qubit can exist in this weird superposition state. So we could use things like the spin of an electron, particles of light, like I said, photons. Something else I'll talk about today, superconducting circuits, also related to the Nobel Prize from 2025. And then these NV centers. These are all different devices that are quantum systems that can be used to store information in both 0 and 1 states, and that harnesses a lot of power. Now, a lot of people, when I say quantum computer, or if you just go search it on the internet, do an image search, you'll find images like this. And they think that this big tower machine here is the quantum computer. But actually, no. That is the cryogenic fridge to run one particular type of quantum computer. For example, this D-Wave circuit or an IBM device. This is for an IBM. This system here is for an IBM circuit. These are all forms of superconducting circuits. Superconductivity is a quantum phenomenon, and it happens at very, very, very low temperatures. So you see here 0.001 degrees Kelvin. So 0 degrees Kelvin is absolute zero. That's the absolute coldest the universe could be. It means there's no energy, there's no temperature, and so it's 0 is 0. And we are just above that. And that's where you get these really interesting quantum effects. And so this circuit is the actual quantum device that's going to do in this case, computing. And it needs to go into this giant fridge. And some of these fridges are smaller in size, but they have these different levels because they're bringing down the temperature. And at the very, very bottom level here, where the actual chip will go, it'll be almost at 0 degrees Kelvin. So that is not the computer, that is the fridge. All right. And like I said, there's lots of special properties that quantum computers can have that could potentially give them a lot more computational power than our current classical traditional computers. Some stuff you might have heard of. Shor's algorithm. So Shor's algorithm is something that can run on a quantum computer, cannot run on a classical bit computer, and it could potentially hack some of our current public key encryption that we use for like online banking and things. Grover's search. That's a really powerful algorithm. It does exactly what it sounds, a search algorithm. So it's really hard to find information in a database. Classical computers have to look one at a time. Quantum computers have different properties, and so you can do these different algorithms like Grover's search, and you can now speed up a database search significantly. However, quantum computers are not better at everything. There are still some operations that just won't make sense to run on a quantum system, so the future is probably going to be hybrid. So there'll be still a role for the classical traditional computer and even AI computing, and then quantum computing can work alongside. Now, if you want, you can react to this one, either type in the chat or throw up a hand or a thumbs up in your reactions. Has anyone ever heard of this harvest now, decrypt later threat or handle threat? I'm just curious, because this is a very, very important thing that a lot of people aren't aware of. So there are bad actors right now. Okay, we got like one or two. Okay, good thing we're talking about this. There are bad actors that we know right now are collecting encrypted data that maybe they can't decrypt right now, but they are going to store it. And then when they do have a system that can decrypt it, they will hack it. So literally harvest now, decrypt later, or handle. That's the other acronym. And so why a lot of us have been concerned about this for a long time is that a quantum computer, like I said, could potentially hack RSA encryption. That's the type of encryption we use right now for online banking, any kind of online transactions. And so it's based on factorizing large numbers. That's hard to do on a traditional computer, but Shor's algorithm can do it in a fraction of the time. And so when a quantum computer, and we don't have this yet, it's coming, when a quantum computer has enough qubits, logical qubits, to run a full RSA decryption, that day is called Q day. So we've known about these encryption vulnerabilities, plus we know our current encryptions are vulnerable to AI attacks and more sophisticated attacks like that. And so there are encryption methods being invented now. For example, the post-quantum cryptography, or PQC. And so this is like harder math problems that a quantum computer and classical computer are supposed to be unable to hack, right? They're still based on a mathematical algorithm, and so it's not theoretically 100% secure, but it's better than nothing. And then you have quantum key distribution, or QKD, which is theoretically 100% secure, and we'll talk more about that in just a minute. And so like I said, a qubit, it exists in this weird superposition state of both 0 and 1 until it's measured or observed, or disturbed by the environment. So these quantum systems are very sensitive, and it's very easy for them to cross over from being quantum to classical. And so you have to isolate them. For example, these superconducting circuits need to be cooled, right, to a very low temperature, so you're isolating any thermal noise. There's also like electronic noise that can disturb it. So everything has to be very, very quiet, both acoustically and electronically. But like I said, these superpositions that a qubit can have means that a qubit can hold values that a classical bit just cannot have. And this opens up a completely new computational space, which is definitely worth all of the hassle of trying to figure out how to make these circuits work. But just remember that we are still about 5 to 15 years away from an industrial scale fault tolerant quantum computer. So industrial scale would be able to hack RSA encryption. This would be like a Q-day event. Currently, we are predicting roughly 4,000 or more logical qubits would be needed to do that. And when you hear announcements from quantum computing companies and things like this in the news, they're not announcing this level of logical qubits. And logical qubit is different from a physical qubit. And if you want to know more about that, just ask in the questions. So this is a real industry, the quantum computing industry. There's tons of players. You might notice some names on this chart. This is one of the Quantum Insider maps where they break down all the different industrial players and what technology they're working on, whether it's like a neutral atom, a silicon chip, superconducting circuits, photonic qubits, so doing it with light. And you see that quite a few companies are in this superconducting circuits category, including IBM and D-Wave, like I mentioned before. So it's curious, like why that was such a natural progression into the superconducting circuits. Well, a lot of these companies have already established their microfabrication and nanofabrication technologies when making like microchips and transistors and things like this in the quantum 1.0 revolution. And so it's quite natural to then transition into the superconducting circuits, because they're also created on these silicon wafer chips, just like our current circuit boards. However, that's where the similarity from the quantum to the classical semiconductor kind of breaks down. And so here you see a picture of one of the quantum chips. And so the squiggly line is a microwave resonator, and these pads are the locations of the Josephson junctions, which is part of that superconducting qubit that we'll talk about. Before I jump down a rabbit hole, were there any questions about what I just said? I don't see any. I'm not sure. There was something in the chat.
There's one question in the Q&A.
Yeah.
Maybe we can take it now.
Yeah, please.
Does nature leverage quantum effects at room temperature, i.e., without requiring any artificial fridge?
Yes, definitely. There's a lot of different platforms that can be used to create quantum computers and sensors and communication devices. And some of them need to be super cooled and some of them don't. And so there are called room temperature quantum devices. And maybe they are still cooled a little bit, but they're not cooled to like 0 degrees Kelvin. Yeah. Great question. All right. So I promised to talk about the Nobel Prize in Physics, and it's a very fitting topic for all these quantum technologies I'm talking about. And so it was awarded for the discovery of macroscopic, so big, macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. And so what does that mean? So they made a circuit that's actually big, macro, and inside that circuit, they super cooled it down to a very low temperature, and they got it into a state of superconductivity. And when a circuit, electrical circuit, is in that state, it'll show quantum effects like quantum tunneling. And so this cartoon here is part of the Nobel Committee's like press release. And so it's to show what quantum tunneling is. And so when I talk about it, I say the metaphor. It's like your neighbor didn't just knock on the door to come in your house; they just walked through the door. So how often does that happen, right? And so if you were to throw a ball, for example, at a wall in the classical world, it would bounce back to you, right? But in the quantum world, you can have a possibility that the ball will just travel straight through the wall. And in quantum mechanics, this is called tunneling, and it's a real phenomenon, and I'm going to tell you more about it in just a second. So they made a really big electrical circuit that shows these real quantum effects. And like I said, quantum tunneling is when a particle can travel through a potential barrier, even if the particle doesn't have enough energy to do so classically. So according to our classical physics, our Newtonian physics, the physics of the big, that particle shouldn't have enough energy to get through, but it gets through. So there are tons of things in nature and in our technology, both classical and quantum technologies, that operate because quantum tunneling is real. So this is really cool. Did you know that quantum tunneling is necessary for nuclear fusion? Like in our star, in our sun, the temperature and the pressure is actually too low to so for fusion to happen, you have to have 2 hydrogen atoms fuse to make helium. And hydrogen atoms have 1 proton as their nucleus, right? Positive charges repel. Like if you ever have 2 magnets and you have their same poles facing each other, they repel. So there's something called the Coulomb repulsion. It has to do with this electrostatic force. And so classically, according to the classical mechanics, 2 positive particles would have to overcome that Coulomb repulsion, and the temperature and pressure in our sun is too low to explain how that's possible. And so that means the only way that nuclear fusion can happen in our sun is because quantum tunneling is real, and that's what allows the 2 protons to form into a helium nucleus and fusion happens. So the very fact that our sun exists is proof of quantum tunneling, and I thought that was really cool.
Sorry, here's a question
Yes.
from the audience. In practice, what is the average number of the physical qubit needed to encode a logical qubit?
Again, it depends on the platform. It can be anywhere from 3 or 4 to 10 to 100 to, like, it really depends on the platform.
Thank you.
Yeah. But that's why some people say we need like 1,000,000 qubits. They're talking about physical qubits. So this is an image from the original research done that won the Nobel Prize. And it's showing this electrical circuit. And this circuit is about a centimeter in size. And so you have the 10 millimeter scale here, right? And you see here silicon chip with Josephson junction. And so that is the place where the quantum effects are happening. And so, like I said, previously, because in the early 1950s and 60s, as more quantum experiments were being done, because the engineering was catching up, like we only just had the laser in the 1950s. So a lot of these quantum effects couldn't be studied because we couldn't generate the light or the atomic states needed to actually study the effects. And so before this demonstration, quantum tunneling and energy quantization had been studying in previous systems, but they were only with a few particles. And so this phenomenon now appears with billions of Cooper pairs, and I'll explain what a Cooper pair is in just a minute, in this circuit. And so that's why it's a macro quantum effect, because you're now dealing with billions of particles showing a quantum effect. And so this is really cool because this transition from the classical to quantum world, from the big to the small, there's always studies about where is that transition, where is that boundary. And so this was a physically big circuit that's showing a quantum effect. And so I like this cartoon that the Nobel Prize committee has created here. So in a normal conductor, like a wire, right, for electricity, you've got little electrons, and the current that's flowing is because these electrons are jostling along the wire, and they're allowing the current to flow. And so they're going to jostle around, they're going to collide with each other, and they're going to collide with the material itself, the wire, or whatever your conductor is. But then when you get a superconductivity, your electrons, instead of being individual particles, they now join up as pairs. And that's why they're called Cooper pairs. And now they're forming a current where there's no resistance. So if anyone's taken first year physics, voltage equals current times resistance. V equals IR. It's one of the few formulas that I actually do memorize. I hate memorization. So there's only a few that I actually have memorized, and that's one. And so if there's no resistance, that would mean that there's no voltage and there's no current. However, in this weird quantum world, because that is a classical equation, V equals IR, that's classical mechanics. So now in the quantum world, you can cool this conductor down. You now have Cooper pairs, and the electrons are going to move as if they have no resistance. And then it gets even weirder. In the bottom diagram here, they're trying to show how now your entire electrical circuit, it's explained by a quantum state, a wave function that is as if it's one single particle. And so you have this circuit that is now in a collective state, a shared wave function, and that was what was so significant about their experimental and theoretical discovery. And so again, superconductivity, right? Josephson junctions, that is exactly the effects that we use in these superconducting circuits and other forms of quantum tech. And so the Nobel Prize from last year, as you'll see throughout the talk today, it plays a role in all of these technologies, if it's involving superconductivity and things like that. Cool. Yeah, is there any other questions right now?
I have a quick question about something from the first section. You mentioned briefly that there was some things that quantum computers will probably never be able to do better than a classical computer. I was wondering if you could give a couple examples.
Yeah, I mean, if you think of tasks like a spreadsheet, I'm not sure if trying to do something like that would be smart on a quantum computer. Now, analyzing a database for sure, but I've also heard, like, I'm not an algorithms expert, but I've heard that there's some operations, some mathematical operations that are really simple to implement on a classical computer, but really difficult or impossible, not impossible, but very difficult on a quantum computer. I think addition was one of them, but I need to double check with my algorithm expert. Yeah. And like there are rules, there are areas where maybe AI is currently overcome, or there's certain operations where AI does better than our quantum algorithm right now. But that's because we don't have a lot of qubits that we're playing with, and we're still developing algorithms, and we're still trying to figure out what these devices can do. It's like we're at the stage in the quantum computer at the 1950s of our classical computer now, right? So in the next 20 to 30 years, there's going to be a lot of development, and it doesn't seem like it's going linear. It seems like it's going exponential. So that's why we have all these weird okay, it could be in 3 years, it could be in 10 years, it could be in 15 years, we don't know. But at one point, a quantum computer will surpass the abilities of a classical computer. And when we get to that point, it doesn't matter how many AI systems you make, how many power plants you build, a quantum computer is still going to whip your butt.
There's another question in the Q&A before we go on to the next section, I guess, is it's a pretty popular question. Is the human brain a quantum computer?
Yeah, there's a lot of debate about that. If you think about the neurons and all the little tiny particles going on in our brains and like what is consciousness, we start to get into the philosophical areas about that. But in my opinion, I believe that there are quantum effects going on in our brains, and I do believe that um, nature is the best computer. That's why we're trying to make quantum computers. That's why Richard Feynman said, started to talk about what a quantum computer could be. It's nature computing. So I think our brains are quantum computers, but there's no scientific way to prove it yet. Good question. All right. Let's talk about quantum communication. So before I talk about the quantum version, let's talk about the classical version. What is the classical internet thing I'm using right now to talk with you? So it is a global network that's connecting all of our traditional computers, devices. You might have heard of the Internet of Things, IoT. And the internet is connected via optical and electrical signals that are being transmitted through fiber optic cables, copper cables, satellite connections, things like this. So the internet, like I said, fiber optic cable, you see a picture here of something like that. So we have underground cabling, we have under the sea, under the ocean cables to link up all the continents. Classical internet also requires boosters, amplifiers to extend the distance over these vast distances, to extend the signals over the distances. Also, we use things like wave division multiplexing. So why send one message down a fiber if you could send 1,000 all at once? So you just use different colors, but you send them all down the same tube. So again, our classical internet, we have this chart here showing the internet cabling across the world, showing the underground, underwater cables, and there's a length scale showing as a heat map. And so all the portions that are in red are like very, very far distances, like 36,000 kilometers or more. So the internet now travel through the fiber optic cables, like you see in the pictures here, travels through a long distance. And then, of course, we have the satellite network. We have Starlink and all these types of networks, satellite networks that are also communicating our environment. Oops, too many. They're communicating through RF communications, so just classical internet. So now what is the quantum internet? So just like the classical internet where we are connecting up computers, the quantum internet is again connecting up quantum computers, quantum enabled devices, also quantum sensors, quantum communication systems. And so we need to connect users that are going to be more, or it's going to be far, right? And so the problem with classical and quantum light, classical light, you can boost it, you can amplify it. Quantum light, we can't do that. There's a theory called the no cloning theorem, and it means it's fundamentally not allowed by nature to make a perfect copy or amplify a quantum state. So an amplifier is basically a giant cloning machine, and that's not allowed in the quantum world. So if we take our quantum signals, our quantum information, and we send it through fiber optic cable that's going, 40,000 kilometers around the world, we're not going to make it because we can't boost it, because that would be a copying machine. So we got to use other tricks. So for example, there's quantum repeaters, quantum memories, nonlinear amplifiers, because nonlinear amplification is allowed in the quantum world. So there are ways to boost the signals to get further through the optical fiber, because as light travels through the fiber, it's going to be lost a little bit to the environment. And remember when I said at the start, noise is bad, loss is also a form of noise. And so loss means that your quantum signal will start to become less and less quantum, and you'll start to get less and less signal that you can even distinguish between noise and background. And so you have these distance limitations if you're just going to send light straight through fiber. But like I said, we have some technologies that are being worked on right now. However, these other solutions like a quantum repeater, quantum memories, it also requires very complex operations like entanglement swapping. And so I haven't talked about what entanglement is yet, and I will soon. But this is a difficult operation to do. And so engineering-wise, we are still creating these memories and repeaters. So they're not deployable necessarily in the real world yet. So we have, but why do we want to do all this, right? If it's so hard to send quantum information, why bother? Well, think about how powerful your computer is if it wasn't connected to the internet, right? And so also, if you have two distant parties, in this case, let's call one Alice and one Bob, and they want to communicate securely, they need to do that over so they can use a classical connection to do that communication, but they first have to have a quantum link, a quantum connection, so they can establish an encryption key between them. And so that's what QKD is, this quantum key distribution. So it's where two parties, usually called Alice and Bob, Alice the sender, Bob the receiver, and they're going to exchange single photons, so individual particles of light, and they're going to do this in real time. And so every time Alice sends a photon and Bob receives a photon and measures it, the combination of them doing that together generates the encryption key. So it's often misunderstood that people think that Alice has the key and is sending the key to Bob. No, it's her decisions of what quantum states to send and his decision of what quantum states to measure. That combination makes the quantum key. And once they've shared their secret key using these single photons, they now can use that key as like an encryption key in any type of classical encryption. And so, for example, one-time pad encryption is theoretically 100% secure. And so this is how QKD and the security of that key is not vulnerable to solving harder math problems like factorizing large numbers, like Shor's algorithm. The security is based on the physical processes, and it's not vulnerable to more sophisticated attacks. And so you need the quantum internet to actually generate that key between Alice and Bob. You need that network. And so, like I said, one-time pad encryption, it's theoretically 100% secure. It's been used for ages. In the olden days, you literally strap the code on a person and transport that person to the other person to transmit the key. And so now we're doing this without physically moving a briefcase. We're going to do it by sending photons of light. And in case you're curious about how the math, the encryption side works, very simple. It's just an XOR operation. And so in binary, your message is in zeros and ones. Your encryption key would be in zeros and ones. Now, once Alice and Bob have that key, one of them can use the key. They can XOR their message that they want to send securely. That XOR, if you remember bit operations, so if you XOR 0, 0, you get a 0. If you get 0 with 1, you get a 1, etc. And so now Alice, for example, can publicly announce the XORed result, this K secure, because it's garbage. No one can decipher it unless they have the exact key, and which only Bob has. And so then Bob can take that public announcement, XOR it with his key, and get back the message. Because it goes back the other way too. So like I said, it's possible that our current encryption may be vulnerable to more powerful quantum computers due to the Shor's algorithm, but there is a solution, and it's quantum as well. So even if quantum makes the problem, we have a solution to fix it. And the security of QKD is not based on solving harder math problems, and it's just on physical processes. And what I mean by physical processes that guarantees the security, things like this. So the fact that if an eavesdropper was to steal one of my photons going between Alice and Bob, because there is an intercept and resend attack, for example, that eavesdropper has to make a measurement on that photon. And the eavesdropper cannot clone the photon and then try to trick Bob and send a clone to Bob, because quantum information cannot be copied. It can only be transferred. That's the no cloning theorem. Also, measurement disturbs the state. So observation, just like Schrodinger's cat, is it dead or alive? I don't know. I got to open the box and check. So with the photons are in a superposition state of different polarization states, like horizontal and vertical polarized light. And so until the photon is measured, you don't know which it is. And so an eavesdropper measuring the photon disturbs the photon, has affected the light, and then Alice and Bob will know. Also, an eavesdropper cannot just steal part of the photon and run away. A single photon is an indivisible bundle of energy. So it stores 1 qubit of information, or more if it's a multiplex state, like I was talking about before with the different colors. You can have photons that store more information, but if you just take the classic photon, if you just take a regular old photon, it will store 1 qubit of information, and it cannot be split in half. And so you can't steal a little bit and then trick Bob into thinking, oh, I got all my photon. You steal it all, or you steal none. Cool. So that was a little rundown of quantum communication and the quantum internet and QKD. I'm not sure if I saw any questions pop up. Yeah?
I have a question.
Yeah.
We can share the information through classical way, like a method that we have these days, but for the key, we want to use the quantum method. So then the number of the key is proportional to the size of the information that we want to share classically.
Yes, in one-time pad encryption, the message and the key have to be the same length. There are tricks that you can use that you can maintain security, but by using a slightly less of key, shorter key. But the most secure form, yes, it's 1-to-1. Great question. All right. So finally, we will go through what is a quantum sensor. So quantum sensing is when a measurement is done that's been enhanced. It has better sensitivity, more accuracy. It has abilities that just classical sensors just don't have. And this enhancement is due to quantum properties, like using a quantum object, like an atom, an ion, a photon, to do the measurement, or to use different quantum properties like entanglement and superposition and interference. So some examples of properties that quantum sensors can detect right now. And also just keep in mind that all of these technologies are in different stages of commercialization. And in my view, quantum sensors are one of the front runners of being commercialized for a while now. And some of them are being deployed currently in real time in the real world. So it's really exciting. So things you can measure like gravitational fields, magnetic fields, electric fields. We'll talk about that in just a minute too. Single photons. So a single photon detector, like an avalanche photodiode or a superconducting nanowire. See that word's there again, superconducting. A superconducting nanowire single photon detector, or an SNSPD. So that is a device that is really interesting. I didn't make a slide about it, but I should have. Again, using the quantum tunneling and superconductivity. So you put your nanowire, so a very, very thin wire, into a superconducting state. And so that means that there's no resistance. And so there's no voltage because V equals IR. And so even though there's a current flowing, because those little Cooper pairs are flowing as a current, there's no resistance, so there's no voltage. But if a single photon hits that nanowire, it warms up the nanowire by that amount of energy, because the photon carries energy. It transfers that energy to the nanowire. That makes the nanowire come out of the superconducting state. And that gives a voltage, because now there's a current and all of a sudden it's been bumped out of superconductivity, and so now there's resistance, and V equals IR, so now there's a voltage. And so that's how nanowire detectors can detect single photons, and they're really, really good at it. They're really, really good at it, much better than avalanche photodiodes. However, you need cryogenics, whereas APDs can run in room temperature. They don't need cryogenics to operate. So if you have a communication or a sensor device or computer that requires really, really precise single photon detection, you'll usually see the experiments using SNSPDs. Anyways, a little diversion. But again, connected to the Nobel Prize, so I had to say it. There's also stuff like hidden object detection. I actually have another webinar I'm going to do. I'll show you that in a minute. And it's going to be on quantum LiDAR. And so that's like this hidden object detection using quantum devices like quantum sources and quantum detectors to do the measurement. Time. So you've heard of an atomic clock probably, because like GPS, that's based off atomic clocks, but those are the quantum 1.0 technologies. So now we have quantum 2.0 technology clocks. They're even more precise, and they give even better timing signals and a more precise GPS, which is actually very, very important for a lot of applications. You can also have sensors that do very accurate temperature measurements, movement accelerometers, and also gases. So like the list goes on, and I could explain all of these to you, but we will be here forever. So, but here's another bit more of a summary of a list here. And so like things like a portable MRI. So for medical imaging, right? So we have devices now, these quantum sensors, they can be very compact, very portable, very low power. And so things like a portable MRI could be possible. I said before how we can enhance GPS and the inertial navigation system. So that's really important in a lot of areas. There's GPS denied environments where you could deploy a quantum sensor and then you'd be able to connect to your network and know where you are. The detection of gas leaks, remote target detection, radar systems, this quantum LiDAR. So again, we have radar and LiDAR as classical technologies right now. And so if you swap out either the source of the lights or the source of the microwave radiations, if it's radar, if you swap that to be a quantum source, or you change your detector to be a quantum detector, that's how you change it to being a quantum radar or LiDAR. And then you actually get a lot of improvement in the signal to noise ratio that you can get from your measurements. And then there's things like gravimeters, magnetometers, using devices like nitrogen vacancy sensors. I have an example of that coming up. And like I said before, quantum sensors, like single photon detectors, those are really important for other industries like quantum computers that are made out of light and communication devices. Because if you want to communicate between two parties, it's really hard to do that with atoms, for example. Atoms don't travel well in free space. They like to just collide with stuff and get absorbed, and they don't go from one place to another. Whereas light's like, get out of my way, I'm going. Light wants to travel through free space very easily, right? And so there's a lot of advantages to using light for communication. So some examples of why we need these devices. So positioning, navigation, and timing, PNT devices. These are used practically in every industry. So things like healthcare, defense, finance, manufacturing, agriculture, transportation, communication, the list goes on and on. And so we need to be able to measure things like the altitude, the acceleration, the timing, synchronization, things like this. And so if we can get a better sensor that weighs less, uses less power, is better sensitivity, like why not? Also, our current generation of GPS, it's using a device. It could be like a quartz oscillator or like a hot atomic clock where it's not as cold, as precise as our new clocks. And so this means that there's like a jitter, there's like an accuracy limitation with some of our current GPS. And also, when you're trying to link to GPS on a satellite, you could have things like space weather, your adversarial actions from others, like jamming and spoofing. So this can prevent you from getting your signal. So now, whereas a quantum sensor can provide navigational information in a GPS denied environment. Also has improved stability and accuracy over classical sensors. And like I said, it can be better than the conventional GPS, which can make some industries, it can make a really big impact in some industries. They also tend to have a reduced swap, so the size, weight, and power, and that's very attractive for the space industry. So there's sensors like quantum accelerometers and gyroscopes, magnetometers, gravimeters, atomic clocks. Like these are all examples of quantum sensors that are either being commercialized now or have already been commercialized and they're being used in the industries now. And so these devices, they can achieve levels of precision and sensitivity that's just not possible with classical sensors because, again, they're using a different physical device to do the measurement. Also, you can connect different sensors. So another reason we need a quantum internet is to make up a sensor network. If you can entangle or connect multiple quantum sensors, you can improve their reliability, you can improve their accuracy. They're all experiencing common background noise, which then can be subtracted, and that will improve your signal to noise ratio significantly. So I promised to show you what a squid is, and no, it's not a squishy animal or mammal or aquatic life form. Oh, sorry.
Before moving to the next, there is a question.
Yes.
Is using a quantum source for LiDAR or remote sensing practical given how weak their flags are?
Yeah, that's an excellent question. I've recently done a study on some of the most current demonstrations of quantum LiDAR and radar, and while there is some limitations in deploying it in the field because of like the weak signals that you have to detect, there's still a lot of an improvement in what you can measure that it's still being explored. So even though there's engineering challenges to deploying the system, there's still a lot of value in doing that. And so, yeah, it's still like all these quantum technologies, they're still being improved. And also you can swap out, you can keep a classical source, you can keep a bright source of light or radar, and then you can use a quantum detector and you can still get an improvement in your sensitivity.
Thank you.
Yeah.
Also, another question.
Hmm.
Current AI creates computation-based intelligence. Given that quantum is different from AI, is it possible to exploit quantum effects to realize novel types of AI that are not based on computation?
I mean, there's a lot of play between AI and quantum. So it is possible, but using quantum effects to improve AI, I'm not sure about that because again, AI is a classical system. It'd be like trying to use quantum effects to make a classical computer better. It just doesn't work. It's like trying to make a rocket ship better by putting like boat gears on it or something. Like it's different mediums. Yeah.
Okay, thank you.
But AI is being used now to help with quantum circuit development because there's a lot of different also parameters. So whenever they're with like in quantum materials, for example, every time they do a run, like a new run to create a new nano device or something, there's parameters that they can vary before they run the. I'm not a materialist, but I don't remember the names. Sorry, but I know this is true. And so you can use algorithms to help optimize. It's like an optimization algorithm. And so AI right now can help with optimization algorithms, from what I understand. So I know about the play between circuit development and materials and AI. Good question. Almost done the talk. Just a couple more slides about sensors. So, and if people want to know more about the KeySat mission, I have some bonus slides, but I figured I'd run out of time, and I did. So, so like I said, superconductivity plays a role in a lot of different quantum technologies. So in a SQUID, so this is a superconducting quantum interference device. And so this was one of the first electronic circuits to be used that showed quantum effects. And it's been around since like I think the 80s, the 70s or 80s. And so a SQUID is very, very sensitive to detecting weak magnetic fields. So there's an electrical current that's going to be circulating around the superconducting loops. And these are images, physical images of two devices. The one on the left has a 3 millimeter diameter circular pickup loop. So that's the thing that you see in the middle. And the one on the right, it says it's a 8.3 millimeter by 7.5 millimeter pickup loop. So it's a bit more square. It's a bit larger. So the point is you put this device into a superconducting state by supercooling it. Electrical currents will be traveling through around the loops. And an electrical current traveling in a loop it will react to a magnetic field is the easiest way to say it. And so you can detect, for example, the biomagnetic signals that are generated by our brains using these SQUID devices. Also, there's high resolution mineral exploration. So determining what's in the ground, under the ground, we need both magnetic mapping and also gravitational mapping. And so these SQUIDs can help with that. Also magnetic navigation. So if you've ever used a compass, right, you can use the magnetic fields of the Earth to navigate. Well, you can also use a very, very precise map of a magnetic field in your region, and then use a very, very sensitive detector to measure where I am based on the magnetic field information, and then the map plus that information allows you to navigate. Also, there's airborne geomagnetic surveys, and so this is necessary for navigation via magnetic maps, like I just said. And so this is a cartoon showing what a SQUID looks like, roughly. And so this is like a typical square washer SQUID device with an integrated input coil. And so it's very, very compact, very, very sensitive. You can see here Josephson junction. That was the terms I mentioned before when I was talking about the superconducting circuits for computers, quantum computers. So these junctions, this is where the potential barrier is, where where the electrons, the Cooper pairs, will go through that barrier when they're in their superconducting state, and they flow like as if there's no, the current flows as if there's no resistance. And so these Josephson junctions are located along the edges of this slitted washer and bias current. And so this is allowing for very, very sensitive magnetic field detection through the phase coherent supercurrents. And like I said, there's other devices like this nitrogen vacancy centers in diamond, shown here. For example, this is a device created by SB Quantum in Canada, and they can be used in for quantum sensing magnetic fields again. So mining, prospecting, navigation, mapping the Earth's magnetic fields. Also, you can detect submarines and hidden objects using magnetic sensing. And so these magnetometers are using NV centers in diamond to very, very precisely measure the magnetic field that it's experiencing. And so how that works in a very high level cartoony way. So you have a diamond lattice structure. So you have a whole bunch of carbon atoms, and then you knock out a carbon atom and you put a nitrogen atom. And then there's also a vacancy, a spot, an opening right across from that. And so the introduction of a nitrogen atom frees up a single pair of electrons. And so now you can excite this electron pair with a laser. And then when this excited electron pair doesn't want to stay excited, doesn't want to stay in a higher energy state, it wants to relax and go back to its lower ground state of energy. But before it does that, it will interact with the magnetic field in its environment. And so that interaction of the excited electron pair with the magnetic field in its environment will then cause the electron pair to go back to its lower energy state and emit some red light in this case. And this amount of red light and the way that it's emitted from the electrons tell you about the magnetic field in that location. And so you can map the light that's emitted by these sensors to create a 3D plot. And this allows for very precise, what's called tensor gradiometry, to locate and classify different objects. Awesome. So you just had a crash course in all of the different quantum technologies. And I know I didn't officially talk about quantum materials, but all of these devices are based off of the quantum materials. So like the superconducting circuits, the nanowires, the NV centers, these are all examples of quantum materials. So they are really the pillars, the foundation of our technologies.
Right. Thank you very much.
Thank you. I'll show you one more thing. If in case you are interested and want to learn more, I have a lot of different quantum training options, both free and paid. For example, I'm offering some quantum certificates. So there's a quantum for executive certificate with NATE, the Northern Alberta Institute of Technology. These are all online training courses. They actually start next week. And so the non-technical is 4 one-hour courses, and the technical course is the Quantum for Engineers certificate, and they're 4 two-hour courses. So just like how I've explained in this talk today, it's all about communicating at a language that all of you understand, because you don't need a PhD to know what are these different quantum technologies and what are the real use cases going on. I also created a laser demo. I'm very proud of this. If you've ever heard of Young's double slit experiment, it's in my Cubo studio in the basement. And so we've got a laser and it goes through a double slit apparatus. And if there's no observer, right, if you're familiar with the double slit, then you'll get these interference patterns, right? The interference effects. The light acts as if it goes through both slits at the same time. But I've created an observer in the path by using polarization, and this observer is telling me, did the light go through the left slit or the right slit? And because I have that observer introduced, now instead of having an interference pattern, you will physically see in the workshop no interference. It goes away. Now that's other cool stuff. And you might have heard I have an upcoming webinar. So if you want to know more about quantum communication, this is all about quantum communication for executives, the first mover's advantage. I'm going to be talking about, again, what is this quantum threat, what is Q-Day, and then present some real world demonstrations of quantum communication in both terrestrial and space-based. And I have guest speakers from 2 quantum communication companies, VeraCloud and Photonics Foundry. And one more.
Thank you.
One more. I'm announcing my next webinar. So it's going to be June 18th. And this will also, again, targeted to a non-technical audience. And this is on quantum sensing for executives, the advantages of quantum LiDAR and PNT devices. And so again, quantum sensors have been commercialized. They are available now, and they are very powerful. So even if some of the engineering, we're still getting over some of the humps, right, with all these technologies, but there's a lot of power in these devices. So I think it's very valuable to share this. So thank you. That's all my plugs.
Thank you. There are some questions. First, in the emerging field of the psychedelic medicine, I think so.
Psychedelic, yeah.
Could it be that quantum effects are behind the psychedelic?
It's possible for sure, yeah. Because if you think about psychedelics, it's affecting your reality and your consciousness, and if your consciousness is related to quantum, you know. Plus, think about it. Nature is quantum. Nature is fundamentally quantum. So the psychedelic is quantum in nature. So, good question.
Another one, could you tell us more about KISAT?
Yes, I'd be happy to. Yeah. Also, thank you again for listening before I talk about KeySat. Check out my website if you want to learn more. And also, the registration for the webinars I'm talking about are there. And connect with me on LinkedIn. So, what is the KeySat mission? So, KeySat stands for the Quantum Encryption and Science Satellite. This is Canada's first quantum communication satellite mission. And I'm part of the science team supporting this mission. The main objective is to demonstrate a quantum link between the ground and space, and actually distribute keys. So demo quantum key distribution. We have ground stations both in Canada and around the world. So there's a Canadian science team and an international science team. And the main mission objective, or one of them, is to distribute quantum keys between 2 quantum ground stations that are at least 400 kilometers apart. And why 400 kilometers? Again, there's that distance limitation of how far you can send quantum information in optical fiber. So if you have 2 ground stations that are located at a distance like this or further, you really need to connect them via satellite, not the ground. And so we're going to be using transmitter telescopes on the ground, and the receiver is going to be on the satellite because it's an uplink. It's primarily, so it's a very compact 8-inch refractor telescope. You can see some of the images here of the original prototypes when the teams were testing at IQC what would best be used in this airborne experiment. And we're going to use 2 quantum devices. So there's going to be, for the uplink sources, there's going to be a weak coherent pulse source. So there's no entanglement in that one. It's a laser that's been turned down in intensity so that every time it pulses a pulse of light, it has on average 1 photon. So it's a weak coherent pulse. And then there is an entangled photon source as well, an EPS. And so this will be an entangled photon pair. So the 2 photons are entangled. One's at the pass band, the receiver band for the KeySat mission, which is in the red zone, red light, 780 to 795 nanometers. And then the other photon is at 1550 nanometers at the telecom wavelength. And so we can send, for example, one photon, one entangled particle to the satellite, and we can keep the other one on the ground, either as a heralding source so that we know the other photon went to the satellite because we have the other one. It heralds the existence because they're entangled. Or we could send the 1550 pair photon into a fiber optic cable and show entanglement distribution, for example, between satellite and the ground or other protocols. So this whole mission is to study quantum lengths. We also can look at entanglement in relativistic settings because the satellite is moving very quickly as it's flying over our heads. So as you're sending up entangled photons, they're being received by a satellite that's moving in relativistic settings. And so you can do some cool science. It's going to be a LEO microsatellite, so in low Earth orbit, roughly 500 kilometers above the Earth. It's around 100 kilos, and it's an uplink. The receiver on the satellite, as you see from this cartoon, the primary receiver here is a 25 centimeter receiver. It's a 4-state polarization analyzer. Again, the red passband, so 780 to 795. The satellite will also have a downlink source at 850. It's going to be a weak coherent pulse source, and so it's not an entanglement source on the satellite. It's going to be a quantum semi-classical source, like a quantum source, but with classical laser light. And we also have, like I said, multiple ground stations in Canada. There's going to be a primary at the CSA, a secondary at the University of Waterloo, and then also a tertiary at the University of Calgary. And they will be the primary receiver for the 850. They already have a quantum ground station at University of Calgary at the observatory, and they've been linking with other missions. And so they're going to be being a primary receiver for that downlink. And like I said, because this is an uplink, we can do lots of cool stuff on the ground. As long as the light that we send up to the satellite is in that passband, then we can swap in different types of quantum sources. We can demonstrate a link to a ground-based atomic memory. So quantum repeaters, quantum memories, so helping demonstrate basically the fundamental building blocks of a quantum internet. And then we also can try out like deterministic quantum dot sources. So when we create single photons, it'd be really nice if we could just push a button and get a single photon. Right now, it's usually probabilistic. You turn on your laser and then photons start coming, but probabilistically. You don't have an on-demand. So with quantum dots, you can get an on-demand source. And so we want to try different quantum sources on the ground to see which ones are better for the link. Yeah. Cool. I see a potential question.
You have a question? The uplink configuration is more troublesome to realize given that the source experience at atmospheric turbulence in the near field. Why not operating in downlink?
Yeah, that's a great question. Thank you, Benvenu. And so basically, there's a lot of advantages and disadvantages to operating in an uplink versus downlink. A majority of the quantum missions were done so far as downlink for this reason, so that the majority of the light will go through space before it gets to the ground in the messy turbulence. But there's a lot of advantages for our uplink because, like I said, we can improve our technologies on the ground. Whereas if you launch whatever technologies are launched on the satellite are static. We can't just capture the satellite and switch out the quantum source. And so even though we do have turbulence that we have to get through on the ground before we get to the satellite, we can compensate for that using adaptive optics and also adjusting our quantum sources. So, yeah. Great question.
Thank you.
Awesome.
Thank you.
I can stop recording and take any other questions off the record if you'd like.
Also, there is a question in the chat box.
Okay, let's do that.
I do see a contradiction between the no cloning theorem and the possibility to make quantum repeater. Can you elaborate?
Definitely. So like I said about it's hard to get an on-demand quantum source. So the reason quantum repeaters work is because it's probabilistic. We're not cloning the quantum state. We are using entanglement, and I do have diagrams, but I don't have them ready right now. But this is the kind of stuff that I teach in my trainings. So when I talk about how a repeater works, you're using quantum entanglement to move the entanglement along a chain. And so as you entangle photons and measure them, you consume those photons, but then other photons that you've now entangled survive and move it along. It's easier to explain with a picture. But you don't violate the no cloning theorem, mainly because, like I said, it's a probabilistic thing. And so sometimes your quantum memory might fail. And so basically that's one of the reasons it works. But it is allowed, I promise. It's been demonstrated. Quantum memories, so there's been a demonstration in China of 3 quantum memories, quantum repeaters, deployed on fiber optic networks that communicated shared entanglement, and they verified the entanglement between that they could entangle any 2 quantum memories out of the 3. Yeah. And is a very, very important fundamental building block to quantum networking. If we can't figure out repeaters, it makes the ground infrastructure networking a little more challenging. Yeah. But you can still do a lot in fiber up to 500 kilometers without requiring any repeaters. So like there's a deployed fiber optic cable network in New York. And they have demonstrated polarization entangled photons that were distributed. The entanglement survived. It was like 99% fidelity at the other end. So like 100% would be like nothing went wrong. So a very, very good fidelity. And that was over 34 kilometers of fiber. And that was around the metropolitan cities. So there's a lot of fiber optic networks and also free space networks that we can deploy in metropolitan areas and then just connect up different cities via networks of satellites, probably. Good question. Okay. Well, thank you very much. I'm going to stop sharing or stop recording. All right. Thank you.